So now time to look at a few of the homework problems. In this section, as we work through 13.4 homework on the definite integral, we will integrate some of the concepts we picked up in 13.2, which is the use substitution. I'm going to leave some of the simpler forms that were from 13.1 for you to go ahead and integrate and give those a try. Those were similar to the examples that were posted in the lecture video, so we'll see how those go. But I'm going to work through a few of the ones that I anticipate will cause a little bit more difficulty. Let's put it that way. Also, I'm going to show you ones that might look like they would be difficult, but because they say an approximation or estimation, we're going to be actually much easier with a TI-84 calculator or the integration feature of your calculator. So a few sample problems. Let's take a look at this first one. Now, if you think, well, I could just come along and I can plug this into my calculator, go from 6 to 7, you would get an answer and it would be accurate, but it wouldn't be counted as correct because WebAssign wants an exact answer in here. Notice there's no telling you how many decimal places to round it, and if you see this 4 over x, hopefully you recognize that's going to integrate to a natural log. So anyway, we've got to get an exact answer here. So let's integrate this. First of all, let's just think of this as integral of x dx plus, let me just move the 4 out front, the integral of 1 over x dx. So notice how I've separated these into two integrals. This first one, x to the first, integrates quite nicely. It's just plus 1. Again, 1 plus 1 is 2. So this is going to integrate as x squared over 2. This one, 1 over x, or if you want to look at it as x to the minus 1, this integrates as natural log of x. The 4's out front, so it's going to be 4. Okay, and before we were putting this plus a constant, we see that now that we're doing a definite integral, we have these boundaries on it. That is really going to cancel out, so we don't need it anymore. We got to just say, hey, who cares about this anymore, right? What we do instead is we write, we're going from 6 to 7. And the way the fundamental theorem of calculus says, we plug in the 7 first, and then we subtract the function with 6 plugged in. So did I get all of this right? I think, yeah. So what we're going to do is, you notice this is really big F. So we're going to take big F at 7 minus big F at 6. Okay, and this is the function big F. Okay, so we're going to put 7 squared over 2 plus 4 natural log of 7. I think I got something else, but you know, I work so many problems and some days I get them confused. Then we're plugging in 6 for x, 6 squared over 2 plus 4 natural log of 6. Yeah. And now we just go through the arithmetic. 7 is 49. 49 over 2 is going to be 24.5 plus 4 natural log of 7. We're going to subtract 36. 6 squared is 36. 36 divided by 2 is 18. So minus 18, and this minus distributes on through, minus 4 natural log of 6. We can combine like terms, 24.5 minus 18, so that's going to be 2, that's going to be 6.5. Now you could either factor the 4 out or leave it, it really doesn't matter. natural log of 7 minus 4 natural log of 6. I would kind of just leave it that way. And when you enter this one in, again, each question is going to be a little different. This 4 may not be a 4 for you. The 6 and 7 will be different numbers most likely. So you'll have to go through the process. That's why I choose these ones. You'll still need to go through this integration process. And you'll notice all of them will integrate that this part is going to be natural log of x. It just might not be times 4. It might be times something else. And then these numbers will change. So your final answer changes, but you get this opportunity to work through and see, okay, this is going to integrate to x squared over 2. This integrates to the natural log of x. That's going to be the answer that you need to put in. If you turn, this can be turned into a number, but it won't get counted as correct. Okay, and the reason I know that is because I tried, and it doesn't say approximate. So the assumption is they want exact. And exact means you leave the natural log because natural log of 6 is going to be a non-repeating decimal. Okay, get it? Got it? Good. Okay, so now this is going to be a similar type situation. So they want to evaluate the integral. They don't say they want an approximate, so we have to assume that they want an exact answer, which means once we find it, we'll plug in the 0 and the 3 for x, and we'll probably be having an answer e to some power, and we will. Okay, so first of all, we just want to look at integrating e to the minus x. One way to do this is to, like we did in 13.2, is do a u substitution. So we're going to let u equal the exponent, minus x plus 5. And then we take the derivative of both sides. Du is now going to be negative 1 times dx. Okay, derivative of 5 is 0, so it's negative dx. Divide both sides by a negative or multiply both sides by a negative. What you get is that negative du equals dx. Okay, so the dx becomes negative du. So put the negative out here. We'll put the du here. E to this becomes e to the u. And so this is all we have to integrate. E to the u integrates as e to the u. This negative multiplies down there. So you might have just said that, you need to go put a negative on it. And then again, instead of doing the plus c thing, we're going to put the limits of integration. I should put them here too, but you can get a little sloppy from time to time. So that's our limits of integration. And so, but remember, these limits are in terms of x, and what we have is in terms of u, so we need to back substitute is what I call it. I don't know, maybe I'm right, maybe I'm wrong, but it's e to the, so maybe it's kind of like not a good idea to put these guys here yet, because these are not u's, these are x's. Let's do our back substitution first. Let's not forget the negative that's in front. And now let's put our limits of integration. Okay, get it all nice and clear. And again, what the fundamental theorem of calculus is this is some function big F of x, and the fundamental theorem says we take big F at 3 minus big F at 0. That's our limits. So let's go ahead and do that. The first one is going to be minus e to the minus 3 plus 5 minus e to the minus 0 plus 5. So sort of think of this is up here. So let's do the arithmetic. Negative 3 plus 5 is going to be minus e to the positive 2. This, a minus and minus makes it a plus, and it's just going to be 5 plus 0 is 5. There's our final answer. No plus c, right? Because it's all taken care of. If there was the plus c, it would have canceled out. this is our final answer. But we need to enter it in because if you calculate this, you get a non-repeating decimal, and they don't ask for an approximate answer, so we got to enter it this way. This is one way to test that we know how to take those to do the to find the antiderivatives. Okay, so again, tying in a couple different sections that we've been working on, but now that we've got the fundamental theorem of calculus, we can actually get an exact answer. Okay. Here's another one, and again, I want to show you this. Your numbers will be a little bit different, the 4, the 3, the 2, but what I want to do is this is going to be a U substitution job here. So remember on these ones, since x squared is down here, remember derivative of x squared is going to be 2x. That's sort of what's up there. So we're going to let u equal the denominator. Okay. So the first part is this is really going right back to section 13.2, getting a little bit more practice on it, which is really good because as we move forward, we're picking up previous stuff as well, and it just practice. You get it down, you'll understand. So we take the derivative of both sides. Derivative of u is 1 du or just du. Derivative over here, derivative of 2 is 0, so that's gone. Derivative of x squared, the 2 comes down in front. Subtract 1 from the exponent, that's x to the 1 power dx. Remember this, we've got a dx here, we want to substitute for it, so we've got to solve for dx, divide by 2x, divide by 2x. So we'll rewrite this as dx equals, I like to do it this way, 1 over 2x du, because we're going to separate these babies. We're going to put the 2x with the 3x so we can get some canceling. We're going to put the exchange the dx for just the du, but this whole thing goes in for dx, but they're going to go to different places. Okay, so let me keep going down here. So let's make our substitutions, right? X squared plus 2, that's this part here, becomes u, and notice it's in the denominator. So I'm going to have this integral. I'm going to have 3x. I'm going to move it sort of to the front. I can't take it all the way out yet because it has a variable, but I'm going to put it sort of in the front part, and then I'm going to write this as 1 over u. dx, I'm going to put this as du, but to do the full substitution, I need 1 over 2x. Where am I going to put that? I'm going to put it over here, because that's the like term it's going to be interacting with. Let's put it that way. So the x's cancel. I've got this 3/2 that now can come up front because there's no variables attached to it. It's just a number, 3/2 being multiplied. It's a constant multiplier. 1 over u du, and this is just a simple integration. It's just the natural log of u. It's one of the ones we had to memorize. So it integrates to the natural log of u. I guess probably have to have absolute values around it, but in the end, since we're going to be making substitutions in here, we're going to be okay. The absolute value, just make sure it's positive. And then we've got the constant multiplier, 3/2. And again, the last step, we want to do the back substitution. We want to replace u with x squared plus 2. So the function we're going to be dealing with is 3/2 natural log of x squared plus 2. Okay, that is our big F function. This is our little f. Again, we could have graphed this and gone from 0, used our tool, but it would have given us an approximate answer. We need to get an exact answer. So we take our function, we take f, big F at 4 minus big F at 0. So this function here, we're going to have 3/2 natural log x squared, so that's 4 squared, plus 2 minus 3/2, that's from down here, natural log, right, of x squared, but x is 0, plus 2. Again, we got sloppy. We didn't put the absolute values, but you're going to see we're going to get positive values, so we don't have to worry about that. So we get 3/2 natural log. 4 squared is 16. 16 plus 2 is 18. Minus 3/2. 0 squared is 0. 0 plus 2 is still 2. Natural log of 2. Now you could also do some funky things. You could move this up, but this is, at this point, it is an exact answer. I guess we should put this. WebAssign will be able to accept it, understand it, and give you proper marks for it. Again, your numbers are going to be different because of here, here, and here. Those are ones that will change. 0 will stay the same, but you'll follow through. Okay, so that's that one. Now, this is the good news, is we've gotten to the place where this one we can actually use because we've got a polynomial function, not a logarithm. It's going to integrate. If we could see here, this is going to be 6x. This is going to be x to the third. So hopefully you see that we're not going to get an exponential or a logarithm, so we won't have repeating decimals. We're plugging in numbers that will get squared or cubed or something. So what we are able to do, see, notice what we're given is a marginal cost function. So this is little f of x. We integrate it, we will get the answer. However, since we're going to end up with no decimals in this, we can also come to our graphing calculator, and we'll see the next ones. It will actually say an approximate answer, so you'll be able to get there. We can graph the derivative. So notice I have not gotten the antiderivative because this process is just getting the actual derivative function. My window, I'm going to have to guess a little bit, but since x is going from 50 to 80, that's helpful. I'm going to want my x window probably about that, so maybe I'll go 45 to, let's go 85. So again, a little bit on each side of the limits so I can see what's going on. I'm not quite sure what to make my y's. I'm going to just see if maximum, the height of the function being 10, if that's good enough. Let's just hit the graph. Not quite, because I run off there. I could probably still get the answer, but I like to see, especially since I'm going to make it 25, and that should hopefully be enough. So yes, now I can see the whole graph. And what I do is I go second calc. I go down to number 7, and it's asking for the lower limit. The lower limit is 50. So let's go back. Lower limit is 50. So what we've really got is we're looking at the integral of 6 plus x squared over 1,000 dx from 50 to 80. Okay, so we could integrate this, but this will work as well. So the lower limit we put in as 50. The upper limit we put in as 80. Again, since that's a marginal cost function, is going to give us the additional cost to go from 50 to 80. It doesn't tell us how many 50 would cost, but we could get that if we needed to. We could go from 0 to 50, and that would give us a cost of producing 50. But what we have is that it costs an additional 309. So this end result is, come on. The end result is that this is going to be equal to 309. Let me walk a little quicker from the integration point. So this would integrate as 6x. This is going to be x to the third divided by 3, 3 times 1,000. So we get 3,000. We get a plus here. So this is our large f function. And again, what we're going to do is we want to integrate this. We didn't have to do any u substitution. We want to integrate this from the limits of 50 to 80. So let's just see if we get the same thing. So we get 6 times 80 plus 80 cubed over 3,000 minus, same thing, 6 times 50 plus 50 cubed over 3,000. Okay. Now you could calculate these by hand. What I'm going to show you, let's come back here. I'm going to turn this one off just to be safe. What I'm going to do is I'm going to graph or put this in and use the table looking up 80 and 50. So I'll show you how to do that. So let's put in this case, we're putting in the large f function. So we're putting in 6x plus x cubed divided by 3,000. No, not times. Divided by 3,000. I'm going to go to table set, and I'm going to change it to ask. And then I'm going to go to the table and watch. It won't show me anything because it's asking. It's waiting to ask me, what do I want for x? Well, I want 80 and I want 50. So I'll put in 80, and then I'll put in 50. And so what this ends up being here, I figured it was going to do that to me. This is 650.67, which is 2/3, right? Minus 341.67. So when you subtract those two, come back here, 650.67 minus 341.67, we get 309, which is what we got up here. Okay, next ones I'm just going to go for that. So this equals 309. So I just want to show you is you could do these either way. We can use the technology. If we don't have the technology, we integrate them, using the fundamental theorem of calculus. This is big F at 80 minus big F at 50. I forgot to write that down. We do that. Again, I just said, well, let's go ahead and use the technology to get these calculated, and we got the same answer. Okay. So now this one, you start reading. I like to read from the bottom, the back. So I see that we're going from June 2007 to 2009. I see as I read backwards, they want an estimate. Cool. Estimate means use the calculator, right? And they want it to the nearest million. So I've got that helps me with the rounding. Then also they give me some information so that T is time in years since 2005. So if that means that in 2005 T was 0, that's really what that's saying. So if 2005 T is 0, that's saying that in 2007 T must be 2, and in 2009 T must be 5, 6, 7, 8, 9, 4, right? You just count it up however you need to do it. So what we're going to do is we are given now, as we read through here, blah, 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 we see the word rate. That's what we're looking for. We're dealing with a rate. This function is a rate function. It is a derivative. So when we integrate it, going from 2 to 4, this is giving us what we get is we get our answer. We get the area under this curve So we can use either the fundamental theorem of calculus, and again, we could integrate this. This becomes t to the third, because you add 1 to it and then divide by the third. This becomes t squared, so 2.6 t squared divided by 2, and you could simplify that. And this simply becomes t, 2.3 times t. And then again, we'll take it from 2 to 4. So you could go through this, you plug in 4 for t, and then you plug in 2 for t, and you subtract those two values. That's one way to do it. And notice we have this newer function, which we'll call, I guess we could use big V, right? Because big V of t. This one here is little v of t. Okay, so the other way to do it is with the technology is just graph this. So let's pull up the calculator, TI-84. And I do want you to get practice doing this again and again, because that's where you start to remember how to do these things. You remember the process. Okay, I need to, right, forget one thing here. Sorry, should make, this is dt, right? The derivative would be emphasized. So we put in this derivative, 1.1. And again, instead of t, we use x because that's what the calculator likes. Raised to the second power. Go over, subtract 2.6 t or x. Not squared, right? Because we're using the derivative function here. Plus 2.3. So just be careful. This is the hardest part sometimes, is we've got two different functions. We've got a derivative function and we've got the integrated function, the function that's been integrated. We've got to know which one we're working with. And in this case, we're working with the derivative function. We're going to graph it and we'll get the area below it. So it's kind of on these two different levels. Remember when we have, well, I'll try not to confuse you too much, but later on we'll talk about those connections. So we'll graph it. We're going from 2 to 4. I probably, need to change my window, right? So let's go from 2 to 4. Let's go from 0 to 6. Here's my guess. I don't know how high we need. Let's just go to 10. The height, the Y max. And let's see if, we see enough sort of, because we're just going to go from 2 until 4. 4, we'll see everything we need to see. Second calc, number 7, or just arrow down, enter. Lower limit is 2. Upper limit is 4. And what I like about this is it shows us what are we getting. We're getting the area underneath the curve. Remember, this curve is a rate. So the area under the curve is accumulation. How much have we accumulated? This is so this is going from 2007 to 2004. We've got 9.5. Let's see. Let's back up. So our answer, this will be 9.53. And again, it's in millions of hours. So that was an increase from 2007 to 2009. That's the amount of increase. But be careful. Remember, they want this to the nearest million. So what we're going to want to round this is we'll round it to 10 million hours per year. So there's 10 million more hours of video. And that's over that 2-year period. Over that 2-year period. Okay. Okay, as we get to this last question that we're going to work for at least now, and we're working through class, I just was wearing my hat backwards one day, actually today, keep my hair down because it's a mess. And I was just noticing we got ASU, but if you read it backwards, it's USA, ASU in the USA. That's kind of cool. Anyway, I don't know, maybe you already spotted that, but first time. So we're going to take a look at this problem here. And what might throw you off a little bit, what sort of threw me off was that I guess we don't need the pin's not working right now, but that they use a capital R. So it's looking like this, and this is talked about annual revenue, not marginal. So we don't think, okay, is this a derivative or not? But annual revenue is a rate of revenue. It's not, again, not the marginal, how much you would make from one more production, but because T is in years, it is the rate of revenue per year. Okay, so since we are looking for an estimate, what this will allow us to do, let's see if I can get this working now. There we go, we're back in business. With our pin there, now we're back in business. So we're going to take this function, and really what we're trying to find, it is a revenue, it's a rate function, 41 e to the 0.094 t dt. Okay, so you could do the integration. What we're doing is we're going t equals 0 represents 2004, looking for an estimate, and we're going to round it to the nearest 10 billion. We're starting in year 2005, and again, that will change for you. So what is 2004 to 2005? That's 1. So if that's t equals 1, what would year 2010 be? That's going to be 2004 to 10. That's going to be t equals 6. So our limits of integration are from 1 to 6. We're finding the area under the curve. So let's just do that this way. We'll enter our function. Again, this is a rate function. So we put in 41 second e to the x, 0.094 x. That's all we need to put in. We're going to, let's check out, we're going from 0 to 6, so let's check our window. We're going from 0 to 7 here, from, sorry, 1 to 6. 0 to 7 will work. We've got it currently set at about 200, which I'm going to leave it at that. I think that'll be enough. We'll graph, we don't need the table. And we want the area under the curve from t equals 1 to 6. So we go second calc, number 7. The lower limit is 1. Enter the upper limit, it asks for is 6, so I put in 6. And it gives me the area under the curve is 287. 287.49, but they want us to round it to the nearest 10 billion, and this is in billions of dollars. So this is 290 billion. Okay, so that's what you're going to want to put in. So they accumulated their revenue, their total revenue from 2005 to 2010, 5 years, was $290 billion. Okay, so that's that one. Enter that in. But I wanted you to do that because it kind of threw me off. It's a big R. Is that already been integrated? And I just find these. But annual revenue, annual is a per year revenue. Per, whenever you hear that word per, that's a rate. That's a derivative. Okay. Keep up the good forward progress. Remember, take the time now to focus as much as you can. The better you do on that final exam, the better overall grade you're going. A number of you still have the possibility of getting an A, but you might need to get wherever your current grade average is, you're going to need to get above that. So if you're at 90 and you get a 90, okay, you're okay. But if you're below 90, you've got to get up maybe 95, 97%. And it's doable. There's people that are doing that are getting, so the first test we did have a few hundreds. Second test, we did have some 99s and some 98s and quite a few 95s. So it's all doable. Focus on this last sections, Okay, so we've got this week, we'll be covering some more. We had next week of new material, and then we got a whole week, actually a week and a half, because we get into finals week. We got a lot of time to review. Focus, work hard on this, and you can make it happen. This is a very special opportunity we have. And again, I know it's difficult, but let's turn lemons into lemonade, right? Let's make things work good for us, because we don't have to take a comprehensive final. That's a good thing. We don't have to go back to learning about limits again. We just keep moving forward with this integration, and we're going to be all good. Okay, keep up the good work. Check in with me, post any questions you have, and we'll all be well. Thanks.